This video will serve as a review for our upcoming midterm. Actually, it's the midterm for last semester, that is for spring 2020. So I'm just going to call it like solution. This is for spring 2020, first midterm, format 242. This is 20 here. So we'll be looking at the questions and seeing how we can solve the problems in here. It's just to kind of remind you of the things you've done and how you can approach the problems when you see them in an exam. The number one question has this. We are given this function as a graph, and the first question asks us to find the f inverse of 3 or the approximate value of that if needed. Now recall that for the function f, which is shown by this graph here, this is my f. The x-axis is the domain. This is the x-axis. The y-axis is the range. But then if we find the inverse function, which we can find by drawing a straight line like here, and then the line y equal to x, and then drawing the f inverse. If we are able to do that, we find that the domain of f inverse will be the y-axis, while the range will be the x-axis. So when they say we should find the f inverse of 3, we are not looking at the x-axis because that's not the domain of f inverse, but we're looking at the y-axis. So this is my 3. My f inverse of 3 will be the value of x when y is 3. So if you check here, f inverse of 3 is actually equal to 0.25. That's pretty much very straightforward and easy. So let's move on. The next question asks us to find which values of the following is closest to the derivative of f inverse with respect to x at 5. Now this notation here, usually I'll write this myself as f inverse or prime of 5. Two of them are the same. So how do we solve this? Well, note that the formula for f inverse prime of 5 is equal to 1 over f prime of f inverse of 5. So then we now need to find f inverse of 5 and f prime of that. Pretty much it's very easy for us to find f inverse of 5. So I'm going to look for that. I'll look at 5 on the y-axis, trace that down to where it touches the graph to find the corresponding x value. So this would be 1. My f inverse of 5 is 1. At this point now, I'm going to find the f prime of 1. However, the function f is not defined algebraically, so I would look for the approximate value of that from my graph by drawing a rectangle. So I'm going to draw a tangent line from here. Tangent line should look like this, I guess. Approximately this. If you have a ruler, you may get a better drawing. So if I draw this tangent line here, it comes, oh, this doesn't look good. So if I draw this, it should come like this. This should actually be a straight line. But basically, yeah, it likely would be, this would be the tangent line. So I'll complete this as a right angle triangle to get this here. So here I have like my x1, y1, the coordinate of this point, and the coordinate of this point is x2, y2. So my f prime of 1 is approximately equal to the slope of this graph of this tangent line at 1. And that would be y2 minus y1 all over x2 minus x1. This will be equal to my y2 here is 7 minus my y1 is 3 over my x2 is 1.5 minus my x1 is 0.5. If I do that subtraction, I'm going to get 4 over 1, which is basically 4. So my f prime of 1 is approximately equal to 4. That tells me that this here will approximately be equal to 1 over 4. So if you check from the option we are given, it's actually the second or the fourth option that is the right solution. So you could circle your answer or mark it good. You could circle it this way or mark it good, though basically I'm not going to give you an option. In my own exam, you figure it out by solving. Let's check out the last question they asked here. They asked which of the following intervals most closely resemble the domain of f. The domain of f is the y-axis. So if you check the y-axis, it goes from 0 to almost 8, though not quite at 8. So we'll see, it goes from 2 rather, from y equal to 2 to y equal to 8, almost at 8, but it didn't get close. It stops at this point here. But let's see the one that closely relates to that. So if you check, you see we have 0 to 2, it's not this. The second one is 2 to 7.8. It's this one because we started from 2 and almost got to 7.8. It's not quite at 8, so this becomes our solution. It's very easy for someone to select from 0 to 8, but notice that the y-coordinate goes from 2 to 8 and not really even from 0. And the graph doesn't even get to 8, it stops at very close to 8, but not quite at 8. So 2 becomes the option. Moving on here, the second question asks us to differentiate this function. Now, to differentiate this function, I think one way you can do it is by solving it as a function of a function. So probably I'm going to let my u to be equal to 3 to the power of x. This means that my du dx is equal to 3 to the x ln of 3. And if my u is this, I have that my y now is going to be equal to cosine inverse of u. And cosine inverse of u dy du, if you differentiate cosine inverse of u, you're going to get negative 1 square root of 1 minus u squared. So by function of function, we have that dy dx should be equal to dy du multiplied by du dx. This should be equal to, my dy du is negative 1 over square root of 1 minus u squared multiplied by du dx is 3 to the x ln of 3. Now writing everything in terms of u, I'm going to get like negative 3 to the x ln of 3 divided by the square root of 1 minus my u was 3 to the x and all squared of that. If you simplify that further, if you wish, if you don't, this is enough at this point. But if you simplify it further, you're going to get 1 minus 9 to the power of x, and this becomes your solution. Now, for this problem here, the easiest way for us to differentiate this number 3 is by using log differentiation. So if I want to do log diff, how do I do that? I'll take the natural log of both sides, differentiate implicitly, and then write the solution the way it should be. So my natural log of y would be equal to natural log of x plus 1 to the power of sine x. However, by the law of log, we have that this power comes down to multiply the log. So I'm going to have sine x ln of x plus 1. At this point, I can differentiate. If I differentiate the left-hand side, I'm going to get 1 over y dy dx, because this is an implicit differentiation, is equal to I'm going to use product rule for the right-hand side. If I differentiate sine first, I'm going to get cosine of x multiplied by ln of x plus 1, plus I'll keep sine constant. If I keep sine constant, I have sine x multiplied by the derivative of this would be 1 over x plus 1. If we differentiate x plus 1, we just get 1. So this is just what we're going to get. This tells me that my dy dx is now equal to what I get when I multiply both sides by y, which will be y multiplied by cos x ln of x plus 1 plus sine x all over x plus 1. And what was my y? My y was x plus 1 to the power of sine x. So I'm going to have like x plus 1 to the power of sine x, then multiply by this whole thing inside the brackets. Cosine of x ln of x plus 1, and then plus sine x over x plus 1. And this becomes the derivative of this function with respect to x. Now, for this function here, actually, it's easier for you to differentiate natural log than for you to differentiate log ordinarily. However, you can actually differentiate log ordinarily. It's not too difficult to do. So to differentiate this, I'll kind of go through the route of converting everything, changing the basis to natural log. So if I change the basis of log x base 2 to ln, I'm going to get ln of x divided by ln of 2. If I change log x base 7 to natural log, I'm going to get ln of x all over ln of 7. If I divide top and bottom by natural log, I'll get 1 over ln of 2 divided by 1 over ln of 7. And that is the same thing as the natural log of 7 all over the natural log of 2. So that tells me that basically my y is a constant, so my y prime is going to be equal to 0 because it's a constant. Natural log of 7 is a number, natural log of 2 is another number, and when you differentiate the constant, you get 0. If you use quotient rule of differentiation to do this, you get an expression that is a little bit complicated or too big, but when you simplify it, you're still going to get the value 0. So either way, you're going to get 0. But this tests your ability to see that you actually know how to do change of basis formula, because it's easier to differentiate in natural log than any other base of log. Moving on, let's look at this problem here. This about radioactive growth, or actually exponential growth and decay. And this is a radioactive decay problem. We are given that this fossil is found as a radioactive carbon and decayed to 15% of its original amount. If we assume that the half-life is 6,000 years, how old is the fossil? Now, the half-life, if you remember, is the time it takes for half of the initial amount to reduce to half. Ordinarily, by exponential growth and decay, if we assume that m0 is if we let m0 be the initial amount of the fossil and then let T1/2 be the half-life, T sub 1/2 be the half-life. Then by exponential growth and decay, at any time t, we have that m of t is equal to m naught exponential kt, while this k is the decay rate, where k is the decay rate. Okay, so now we need to find k. Actually, the value of m naught is not too important. We are given that the half-life of the substance is 6,000 years. That tells me that m of 6,000, which is the same thing as m of t1/2, is equal to 1/2 of the initial amount, which is m naught. But then m of 6,000, if you plug it into this formula here, we are going to get that m of 6,000 would be m naught exponential 6,000 k, and this value is equal to 1/2 m naught, which is the same thing as m naught over 2. Since the initial amount is not 0, we can divide by m naught. If we divide by m naught, we'll get that exponential, this not equal to this, implies here exponential 6,000 k is equal to 1/2. To find k, we take the natural log of both sides. If you take the natural log of exponential, it cancels out because it's the inverse. We just get 6,000 k is equal to the natural log of this side will be the natural log of 1/2. Natural log of 1/2 is the same thing as the natural log of 2 raised to the power -1, and this is the same thing as negative the natural log of 2 by law of logarithm. So this tells me that my k is what I get when I divide both sides by 6,000. So that's going to be negative ln of 2 divided by 6,000. Now we found k, and then we can now move forward. Now let's say, suppose it takes t star years for the fossil to decay to 15% of its original or initial amount. So now I want to find what that t is. This means that the amount at t star is the same thing as 15% of the initial amount, which is m naught. 15% is the same thing as 0.15. That's 15/100 m naught. This implies here, what is my m of t star? This implies my m of t star, if I plug it into the formula for exponential decay, that would be m naught exponential k of t star. And we say that this is equal to 0.15 m naught. Now, since m naught is not 0, we can cancel out m naught from both sides to get that our exponential kt star is equal to 0.15. To find what my t star is, we already have our k. To find what my t star is, I'm going to take the natural log of both sides. And if I do that, I'll get that my kt star is equal to ln of 0.15. That means that my t star is going to be equal to ln of 0.15 divided by k. What was my k? My k is 15 was negative ln of 2 divided by 6,000. If you simplify this, you get that this is equal to negative 6,000 natural log of 0.15 divided by the natural log of 2. And this is in years. This answer is enough if you are solving this in a test because you're not allowed to use a calculator. However, if you simplify this, if you point this into a calculator, you're going to get approximately 16,000 years, about 6421.8 years. Now, let's think about this conceptually. In fact, let me conclude first. Therefore, it will take about negative 6,000 ln of 0.15 over ln of 2 years for the fossil to decay to 15% of its initial amount. Now, let's think about this. We got that this value was 16%. I'll write something here and erase it. Let me just make some comments here so you can see this conceptually. The half-life of this substance is 6,000 years. That means after 6,000 years, we're going to have 50% of the original, 50% of the original M0 left. That is 1/2 of this. After another 6,000 years, then we're going to have only 25%, which is half of this, left, M0. After another 6,000 years, we're going to have 12.5% of this left. So here we are looking at something that a little bit before this time, that's somewhere in this amount, at this point. Now 6,000 plus 6,000 plus 6,000 is going to give me 18,000 years. However, we're looking at a time interval at this point. So it's between 12,000 and 6,000, but it's between 12,000 and 18,000. And it's a little bit closer to 18,000 because 12.5 is closer to 15 than 25. So you see that the value we got, which is 16,000 something, is actually very accurate conceptually if you think about this in terms of half-life. I just wanted to make this comment here. It's not really necessary, so we'll move on. Okay, now let's go ahead. So here we are asked to find the limit of a function. Now for me to find the limit of this function, I could actually go this way. I can let my u to be equal to 1 plus square root of x over 3 minus x. Now this means here that my limit as x tends to infinity is equal to the limit of this whole function the limit as s goes to infinity of 1 plus square root of x over 3 minus x. Now, if you take the limit of this, you're going to get like infinity over negative infinity, and that would be basically indeterminate form of type infinity over infinity. So then we can apply L'Hopital's rule. If we apply L'Hopital's rule here, we are going to get that this will be the same thing as the limit of, if we differentiate what we have above, derivative of 1 is 0, derivative of square root of x will be the same thing as 1 over 2 square root of x over, if we differentiate 3 minus x, we just get negative 1. Now, if I take the limit of this, I'm just going to get 0. Negative 0 is just 0. So that tells me that as x tends to infinity, my u tends towards 0. Therefore, the limit as s goes to infinity of arc sine, actually I prefer to write my arc sine this way. You can write it any of the ways. Sine inverse of 1 plus square root of x divided by 3 minus x is equal to, we do the change of variable of sine inverse of, I'm going to change this to u, and then as x tends to infinity, u tends to 0. So this will be equal to, what do you have here? Sine inverse of u as u goes to 0 is basically 0. So in conclusion, the limit as s goes to sine inverse of 1 plus square root of x divided by 3 minus x is equal to 0, and that is that. I'll be solving question 7 before I end this video. I just wanted to make it a 2-part video for the review. So here we are also asked to find this limit, and we are asked to say if we are using L'Hopital's rule or not. So let's go ahead to find the limit as s goes to 0. S goes to 0 of log cos x over x squared. Actually, if I take this limit directly, I'm going to get the natural log of cosine of 0 is 1, all over 0 squared is 0. So I'm going to get 0 over 0, which is indeterminate form of 0 over 0. So now I can apply L'Hopital's rule because I have an indeterminate form of 0 over 0. And if I apply L'Hopital's rule, I'm going to get this. I'll differentiate natural log of cos x. If I do that, I'll get 1. In fact, let me do that. d dx of ln of cos x will be equal to 1 over cos x times negative sine x, which is something as negative sine x all over cos x, which is equal to negative tan x. So the derivative above would be the same thing as negative tangent of x all over, if I differentiate what I have below here, I'm going to get 2x. I'll erase this, please. Now, if I differentiate or take the limit of what I have here also, I'll get indeterminate form of type 0 over 0 because tangent of 0 is 0 and 2 times 0 is 0. So I'm going to apply L'Hopital's rule again. if I apply that, I'll still have limit as x tends to 0 of when I differentiate tangent, I get secant squared over if I differentiate this, I get 2. Now, if I take the limit of this, actually the limit of secant is as x goes to 0 is 1. So this is going to give me like -1 over 2. And that becomes my limit. So in conclusion, the limit as s goes to 0 of log of cos x divided by x squared is equal to -1/2. So this will be the end of this part of the video. In the next video, I'll solve the following or the remaining problems in this midterm.